This is Grand Admiral Rosine, following the physics directive to explain conceptual modern physics. In this video, we will explore Einstein's equivalence principle. We will begin with a quick review of Newton's universal law of gravitation. Similar to Galilean relativity, this is a classical law but will be replaced by Einstein's general relativity. According to universal gravitation, gravity is a force that causes the attraction of all matter in the universe. But it has several conflicts with special relativity. First, since mass is just a form of energy, all energy should be attracted to each other. This is not incorrect, as we will discuss later, but it does reveal that reforms need to be made to our understanding of gravity. Second, the force of gravity scales with mass, creating a constant acceleration. If a spaceship approached a massive body near the speed of light, the gravitational pull could accelerate it beyond that speed. Third, it assumes that, if an object moved, it would instantly change the gravitational force experienced by every object in the universe. But since space-time is relative, this would break causality since information can't exceed the speed of light. General relativity solves both of these problems with the equivalence principle. To understand it, imagine a person floating in a spaceship. The spaceship then accelerates upward, catching up to the person and pushing them up as well. From the person's perspective, they would seem to have fallen. This creates what is called a fictitious force, which is a force that seems to exist in accelerating reference frames, but isn't caused by any real physical interaction. For example, when speeding up in a car, it feels as though a force pulls you back in the opposite direction of the actual acceleration. In the spaceship scenario, the fictitious force seems to pull the person to the floor of the spaceship. Now imagine a person standing on Earth. They don't feel as though the top of their body is pushing the rest down against the floor, sandwiching them, because every particle in their body is accelerating close to equally. Instead, they only feel a force from the ground pushing them up. This is identical to how they would feel standing in the accelerating spaceship. According to Einstein's equivalence principle, these two situations are identical. A falling object, if we ignore air resistance, is not accelerating. Instead, the ground and everything on it is accelerating upward from the object's local spacetime curvature. This is because gravity is not a force. Instead, it is the curvature of spacetime. On a spacetime graph, we can draw geodesics, the shortest possible paths an object could trace through spacetime. In flat spacetime, which is spacetime without gravity, these geodesics are straight. Therefore, geodesics are the paths taken by an object moving at a constant speed. But energy curves these geodesics, causing a particle following them, therefore moving at a constant speed within its local spacetime curvature, to appear as though it is accelerating from flat spacetime. This is why, to satellites, objects still seem to be falling. They are further from the center of the Earth, and so spacetime is less curved. As a result, the object in free fall disagrees with the satellite on who is accelerating. Even though it seems like the object is falling to someone on the surface, it's actually taking a straight path through spacetime. Those on the surface are the ones accelerating, just like if it was a spaceship. This is not refuted by the Earth's round shape. You see, spacetime is curved so that objects seem to accelerate towards the center of the Earth from flat spacetime. For this reason, all of the matter around the center is pushing on each other, shoving the Earth's surface and everything on it outward. This is why, technically, the Sun revolves around the Earth from the perspective of the Earth's local spacetime curvature. To be clear, this is not a conspiracy theory, but a scientific technicality. The Earth views itself as moving along a straight geodesic, but the Sun's gravity curves it. Let's now view the situation from the perspective of Earth's local curvature. The Sun accelerates towards the Earth, but the Earth moves to the side at a constant speed. Since the Sun is always accelerating towards Earth, it ends up orbiting it. Interestingly, the Sun is also orbiting everything else in our solar system from their local curvatures. If we now account for the Earth's gravity and view the situation from the Sun's local spacetime curvature, we realize the Earth orbits the Sun since it curves spacetime around the Sun and accelerates towards it. From flat spacetime, we observe something closer to the model created by classical gravitation. Objects in the solar system orbit the Sun, and the Sun slightly orbits them. This solves all three problems with Newton's universal law of gravitation. The first one is solved since all energy curves spacetime and all energy is affected by it. To see how it solves the second issue, take the person in the spaceship. The spaceship is what is actually accelerating. As it approaches the speed of light relative to the person, its relative mass would increase. This would decrease its acceleration, preventing the spaceship from reaching light speed. It is identical with gravitation. As the surface of the Earth, for example, approaches light speed, the surface would increase in relative mass and undergo lower accelerations. For this reason, no object in free fall will ever exceed the speed of light relative to an observer in flat spacetime, and the surface of no massive object will exceed it, since the acceleration due to gravity is tied to relative motion. Lastly, it solves the third issue, because it takes time for spacetime to curve. Therefore, if a particle were to move, changes in spacetime's curvature would travel throughout the universe at the speed of light. These ripples through spacetime are called gravitational waves. In the next video, we will explore some of the consequences of restructuring gravity, including a form of time travel independent of relative motion. If you enjoyed this video, please give it a like. If you wish to further explore conceptual modern physics, subscribe to my channel and join me in the Physics Directive. Long live the Empire.